Right, today we have Tero Karras from NVIDIA giving a talk that was given in ICARE, I believe, but there is new stuff that we are eagerly waiting to hear about. Welcome, Tero.
Thank you. Hi, so my name is Tero Karras. I work as a principal research scientist at NVIDIA. And today I'm going to talk about our paper Progressive Growing GANs from the ICARE earlier this year. My slides are largely the same that I had in the oral presentation back there, but I have added a little bit extra at the beginning and at the end. Alright, so the problem of generative modeling is such that we are given a bunch of data, like pictures, and we wish to capture the essence of these pictures into a probabilistic model. Once we're done, we can then sample that model to basically produce an arbitrary amount of new data that is supposed to look the same. Of course, the modern approach is to use deep learning, and the most common way you apply deep learning is called supervised learning. There you have a neural network and you're feeding it a number of example inputs. For each example input, you also know the desired output that you wish the network to produce. And what you do is you handcraft a loss function in order to tell how well the network is doing at any given moment. And then it's simply a matter of training the network so that its performance improves over time. Generative modeling is a bit different though. It's called unsupervised learning. The typical choice is to draw the inputs to the network from a random distribution, so that in the case of pictures, any given random input should produce a reasonable looking output image. And so we can sample the random numbers many times and get a collection of pictures. Now the training data is also a collection of pictures, and now the big problem here is already evident, because there's absolutely no correlation between these random inputs and images in the training data. So it turns out that it is actually quite difficult to formulate a loss function that would tell how well the network is doing, because the goal here is not to reproduce any single image from the training data, but instead generate new images that just have the same kind of a look. There have been various attempts to overcome this obstacle by moving things around in this picture, but it's hard because the pieces don't fit together that well. The real breakthrough came 4 years ago when Ian Goodfellow and his colleagues from OpenAI published this radical new idea called generative adversarial networks. And the idea is to actually train 2 networks simultaneously. So what we'll do is we'll replace the loss function with another neural network, and we'll call the one on the left the generator because it's supposed to be generating images, and the one on the right is called the discriminator because it discriminates images based on how realistic they look. And we can now train the generator the same as before. We modify it to improve the realism determination as given by the discriminator. But at the same time, we also need to train the discriminator. And the way we do that is that we show it images produced by the generator, and we modify it so that these images are given low scores. And similarly, we show it examples of the training data and ask it to give high scores for these ones. So effectively, the discriminator is gradually guiding the generated images towards more and more realistic ones. Ever since its conception, this basic idea has spawned a lot of research papers with pretty amazing results. Nowadays, we can turn zebras into horses, cats into dogs, dogs into mushrooms, and frowns into smiles. However, the training process remains quite unstable, and so these results have been largely limited to quite low resolutions. Our goal is to find ways to stabilize the training so that we'll be able to generate photorealistic results and megapixel resolutions. By the way, that is actually not a still picture. You can see her smiling every now and then. But first, we need a deeper understanding of what's exactly going on during the training. And the intuition behind our paper can be explained quite well by looking at this map of the Finnish archipelago. Here, the islands represent real images from the training data in the vast ocean of all possible images. And whatever is produced by the generator can be seen as a distribution here that is perhaps close to the real thing, but not quite there. And now the point of the training is to gradually shift the distribution towards the real thing, so that the training images and generated images would be indistinguishable from each other in the end. Let's take a closer look at one of these dots. Our view of the situation looks like this. The generated sample is represented by this surfer guy who is trying to get to the shore. Everything that happens during training is governed by loss functions. In our case, the improved Wasserstein loss. Gravity is pulling the surfer down, but there's this adversary that is raising waves wherever the surfer is located. However, they cannot raise waves near the shore, and the waters have to be calm in between. These details will be slightly different depending on our choice of loss function, but at the time we were getting the best results using these particular formulas. So what happens is that the surfer is sliding down, but the wave is following them, and so they'll be able to ride it toward the shore. What's the problem with high resolutions then? Well, in low resolutions, this picture is quite accurate, but if we increase the resolution, then both the generator and discriminator become extremely complex functions with shattered gradients, and our picture is no longer accurate. Instead, it's as if we had thrown the surfer in the middle of the ocean. There's waves everywhere, and the shore is nowhere to be seen. Now, we can view the act of decreasing resolution as if we were zooming out. We get a much better view of the big picture, but we can no longer discern the smallest waves and details. So, motivated by this observation, our approach is to start from a ridiculously low resolution 4x4 pixels, so that we'll be able to make progress toward the right direction. Once we get closer, we'll then increase the resolution by adding more layers in both networks. And so we'll keep zooming in as we go, so that we are able to model increasingly fine details. In practice, our generator is made up of these replicated blocks that consist of nearest neighbor upsampling and 3x3 convolutions. We can extract an image out of the network at any point by feeding the activations through a 1x1 convolution. When we want to increase the resolution, we want to introduce these new layers, but we cannot just go and add them, because doing so would cause a sudden shock in the training dynamics, something we'll need to avoid. So instead what we'll do is we will extract two different images out of the network simultaneously at consecutive resolutions. And then during the training, we'll do a smooth linear crossfade between them to avoid sudden changes to the situation. And once we're done, we can then just discard the lower resolution and keep going. Our discriminator is modeled as a perfect mirror image of the generator, and both networks undergo the same kind of growing and crossfades during training. Let's take a look at how the training behaves with and without this kind of growing. So on the left we have a traditional fixed resolution training scheme where the generator is outputting 1K by 1K images all the way through. And on the right we have progressive growing. So looking at the video, I would say that with fixed resolution, the progress is somewhat chaotic, and it's not always clear whether the images are improving at all. It's like a dog chasing its tail. But with progressive growing, the images stay reasonable all the way through, and there's a clear tendency towards better and better looking images. There's another difficulty related to the variation of the generated images. What can often happen is that the entire distribution of images flocks toward the same nearest shore in this picture, and we have an effect called mode collapse right there. In order to avoid that, we have to have some mechanism to force the samples apart and keep them apart throughout the training. If we look at the discriminator, it's pretty obvious that our chances of being able to do this are quite low if we are looking at just individual images. So instead, we'll want to be looking at multiple images at once. The idea in itself is not new, but the previous techniques have been kind of heavyweight for our purposes. I should stress that in a situation where we want to generate really high resolution images, we are constantly running out of memory. So we found out that we can actually get the same effect using a much simpler, much lighter weight mechanism, and actually we'll even get better results that way. So what we'll do is we'll introduce this new kind of layer toward the end of the discriminator. The layer receives the activations produced by the preceding layer as input, and it simply passes all of them through as is. But in addition, it also computes the standard deviation over the different images and averages the standard deviations over the feature maps and over pixels to produce a single scalar. That scalar is then appended as a new feature map in the output. And the surprising thing here is that even though we're computing just a single value, apparently this is enough to ensure that there's enough variation in the generated images. There's one more difficulty. Sometimes the generator can slip up a bit, and in our visualization that could mean that the surfer ends up on the wrong side of the wave. What happens next? Well, gravity is still pulling them down, and the wave is still following them. Boo. We don't want that to happen. We have noticed that this kind of effect is always accompanied by a sudden escalation in signal magnitudes flowing through the networks. And if we look at previous techniques, it's no wonder that we can see a lot of normalization techniques being applied to usually both networks, because normalization is a good way to avoid such an escalation. Furthermore, we can see that pretty much all of the techniques employ batch normalization. This is problematic because batch normalization requires huge mini-batches, and we cannot afford them at high resolutions. So what to do? Well, we noticed that it is enough to employ normalization in just one of the networks. It's enough if one of the networks is unwilling to participate in this kind of arms race. So it turns out we can safely leave out the normalization from the discriminator. In the generator, we'll use a new kind of normalization that we call pixel norm, that works equally well on arbitrarily small mini-batches. We perform this normalization at the end of every layer of the generator. And the way it works is that we look at each individual pixel of the activations and interpret it as a vector over feature maps. And we'll process every pixel the same way. And then what we'll do is we'll simply normalize these vectors to produce normalized feature maps. And the surprising thing here is that this kind of normalization doesn't actually appear to harm the generator in any way. We can just do it. And then we don't have the problem of escalating magnitudes anymore. I'll show some results next. These are all images produced by our generator after training it for 4 days on 8 GPUs using a new dataset that we created for this purpose. It's called CelebA HQ, and it's basically a higher quality version of the standard CelebA dataset. Contains 30,000 images at 1K by 1K resolution, and it's available in public. The interesting thing, though, is to observe that the generator is a continuous function. So if we do smooth interpolation for the inputs, then the output images will also interpolate smoothly. And that looks like this. It's funny to see how most of these transitions between different people look quite natural. The orientation of their head is changing, their facial expressions are changing, the hair is growing, and so on. Looking at this, I would go as far as argue that by virtue of the adversarial training, the generator has learned to basically model every single aspect about the human face, and now it's randomizing these different aspects, combining them in new ways and interpolating them. Some of these transitions look kind of weird, though, and at the time it was unclear to us why that was happening. Of course, this is not limited to human faces. We can train it with any kind of image data we want. And here I'm showing examples of 7 different categories from the LSAM dataset. LSAM is a huge dataset, and it's much more difficult than CelebA, because these are basically random photographs and pictures downloaded from the internet, and there's immense amounts of variation in them. But nevertheless, the network learns something reasonable, and many of the images kind of make sense. It's particularly impressive that with the cars and conference rooms, for example, we have pretty valid 3D rotations, and with people and cats, there's lots of zooming in going on, which is pretty natural looking. of course, there's still room for improvement. We are particularly proud that our network was able to learn to generate lolcats by looking at examples, and it even made a valiant attempt at generating some gibberish captions for them. I have no idea what it says, but probably something funny.
So just as a comment, the alphabet doesn't make sense, but you are augmenting the data set by flips as well, right?
That is right.
So have you tried without flips? Would you actually get?
I have. Well, then you do not get this weird looking letters, but of course the sentences make no sense.
Yeah.
It would be funny to try to train the networks with just text, like render images of text from a book or something, and see if it can reproduce something meaningful. We also cover a lot of other things and other contributions in our paper that I will not go into here. I should point out though that during the project we found it extremely important to have some kind of a metric to tell whether the images are getting better or worse when you're tweaking things, because it's extremely difficult for a human observer to look at hundreds or thousands of images and tell, you know, how they look like. Are they getting better? We didn't have a good metric at that time, so we had to invent our own. But nowadays there are better metrics, like the Brechet inception distance, and if you are working on these things, I would actually advise to go with that, not use ours. Our source code is publicly available, along with the CelebAHQ dataset and pre-trained networks and lots of images and videos produced by them. So if you're interested, if you have a big GPU, then you might want to consider downloading the code and, you know, hacking away. We feel that these results are extremely promising, although not perfect yet. So obviously we have been interested in developing these techniques further ourselves. It's been almost a year since our paper came out, and I've been busy with subsequent experiments. There's a high possibility of a follow-up paper, or maybe even two, coming out at some point, so stay tuned. I'll show a quick teaser of our viewer results. So here the networks are actually exactly the same, but they have been trained using a new dataset that I created that consists of just arbitrary photos taken by people that they uploaded to Flickr. And I've transitioned to a better loss function, and overall the images are much sharper than they were a year ago, and there's a lot more variation. Some of the transitions still look weird, but there are considerably fewer of them. Most transitions look, you know, just fine. And what's particularly interesting for us is gaining control over the image generation process. So in its basic form, the generator is a black box. You feed in random numbers and you get random pictures out. But considering, for example, digital content creation, authoring content for, say, games, it would be highly beneficial to gain a better understanding of how the generator is doing what it's doing, and find ways to, you know, get intuitive controls to modify the image. But this is work in progress, so we'll see how it goes. I leave the video running because it's kind of fun to watch, but that concludes my presentation. And if you have any questions, please go ahead. Thank you.
Can you write down the metric function, the new metric function you mentioned, the spelling?
The new objective function?
Yeah.
Well, I'd rather not write it down because, you know, there's a lot of details to explain. But I would suggest that you Google for a recent paper called "Which Methods for Training GANs Do Actually Converge?" That paper contains a lot of extremely useful and insightful analysis and proofs, and it advocates a particular kind of objective. They call it the R1 regularization. So that's the thing I'm using here. It's basically the same old objective that was already proposed in the very first GAN paper. It proves that Wasserstein that we used previously actually doesn't work. And then it also proves that there's one piece missing in the original objective, and just that's it there. Okay?
Would it be possible to gain some intuition on controlling the generative model by doing more of the discrimination? So if you have a set of labeled sub-objects in your images, so could you train the classifier to basically discriminate between these objects and other stuff that's in there, so that you would learn basically which features are controlling for the presence?
Right, so the question was whether we could gain control, more control over the images by using labeled data and external classifier and so on. Yes, we could. The closest thing to that is conditional GANs. So here the training was completely unsupervised. We just had images and no labels or annotations of any kind. But what you can do, and what has been done a lot in the literature, is basically teach the generator to model a conditional distribution. Let's say we have human faces, and we have labeled each face with male, female, young, old, that kind of stuff. Then we will basically be giving the generator two inputs: the random vector label code and the label that we wanted to reproduce, and then drawing the labeled codes from a random distribution, it ought to generate images with exactly the same label as we wanted.
There's also stuff that does this for continuous things like pulses and so forth.
That is true. So in the conditional setting, the label can be a discrete class label, or binary attributes of the image, or it could be continuous values like age of the person, like 3D orientation, lighting, that kind of stuff.
But have people gained actual understanding what happens in the generator, but what features are controlling for appearance of the particular feature?
No. So conditioning is something you can do, but it does not actually reveal anything about what's happening inside the black box. It just gets more involved.
Yeah, it changes the training, true, you don't learn the same thing anymore.
Yeah. Also, one interesting observation is that the mapping from the random inputs or the labels to the image is highly nonlinear. If you, for example, explore the data space by doing linear interpolations, the changes in the image are highly nonlinear. The space is curved in some sense, and that makes it even more difficult to figure out what the mapping actually is. but we believe we have found a way to overcome that nonlinearity.
Just looking at these images, I think, have you tried if doppelgangers sort of appear close to each other? Or is there even a measure of closeness in this space?
You mean how close two images are to each other?
So if you compare some other way of training a GAN versus your method, how do doppelgangers appear in that space and in the space created by your network?
Right. Yeah. So the question is, have we compared to other training techniques, and perhaps other techniques do not suffer from the same issues? Well, when we were writing the paper, we did compare against the state-of-the-art techniques back then. And the problem was that none of the techniques would scale to high resolutions. We could not get them to train with 1K by 1K images. They would just explode and produce, a static image or some garbage. So in that comparison, we actually had to go with a much lower resolution dataset. But even so, the results that we were getting were better according to a couple of objective metrics. But afterwards, there have been a lot of new research and the techniques have improved. So I would say that what we are proposing in the paper is no longer the best way to train GANs. It was the best at the time. And for example, I produced this video using a slightly different set of techniques. So the field is moving really fast and the results are improving. But I would say that there was at least one really important thing that we accomplished with our paper, which is raising the bar. Before our paper, what you would see was mostly pretty bad looking images, if I'm being honest, at very low resolutions that contain pixel artifacts and disfigured faces and so on. And then our paper showed that you can get much better results and you should strive for much better results. And afterwards, there have been many papers that take our data set, train with that, and show that hey, we can do it too.
Yes, question about the data set. It's very nice how much effort you put into that, and you're using some of these spatial landmark features to basically put the nose in the middle and so on. So how much do you feel that just kind of having this spatially consistent data for training, is that a large contribution to why this works?
Right. So the question is about data sets and the observation that we align the faces using facial landmarks, and how much does that have an effect on the quality of the results. It's very important. So, for example, comparing these faces to the random photographs in the ELSAN dataset, there's a clear difference. I would say that the more variation there is in the dataset, the more there is for the networks to learn. That they have to capture all the effects at play in there. And for example, even here we can see that the backgrounds are not so good. The faces are good. Face is always in the same position. The eyes are in the same position. And usually humans have two eyes and so on. But if the faces were not aligned, then you'd have one more dimension, like the orientation of the face and maybe the position of the face. You would have faces that are halfway outside the picture. Actually, you do have some of those here, because many of the photos you find in Flickr are like selfies with two people next to each other, so you have another face, showing partially. And in those cases, it's not perfect. It looks like a mutant. So
one thing to add is that in the tests using the other models, they, even with the same data set, the stuff they produce is not as good, or was not as good, even close. So it is important, but that's not sort of the differentiating factor of this algorithm versus what was there at the time when we did it. That makes sense.
Yeah, and when it comes to phases and alignment, that has been historically the most popular data set to use because it works the best. But now it seems like the next challenge is training ImageNet and competing on the results there. ImageNet is really difficult because it's again random pictures from the internet, and it contains 1,000 different categories of pictures and only 1,000 examples of each. So it's going to be an interesting competition to crack that next.
So with the pixel normalization technique that you developed, right? Did you try the other way now?